This question is asking us to integrate an integral of e to the minus x squared from 0 to infinity. And we're not able to do that integral. And so what we're going to do instead, we're going to call that integral I, and we're going to have that integral times itself, so it's going to be I squared. Just change the variable, so x is in the first one and y is in the second one, but they're the same thing no matter what the variable is. You integrate with respect to x, then you integrate with respect to y. Now these can be combined into one double integral. We have this property that said that if your function is separable and your bounds are numerical, then you could actually do the two individually and multiply the results. And so we have this double integral here, and this is going to be equal to I squared. And this integral we can evaluate. This double integral can be evaluated using polar coordinates. The presence of x squared plus y squared should trigger the fact that polar coordinates are an option. It's set up as dx dy, or it could even been written as dy dx. The bounds are the same, 0 to infinity. And so what? Positive x's and positive y's on out forever. The region is the first quadrant. X's go from 0 out to infinity. Y's go from 0 out to infinity. And we need to do this in polar. In polar, what we do is we execute a radial slice outward from the origin. That's our R slice. And so we go radially outward, but this goes out to infinity. The upper bound on R will be infinity, and the lower bound on R will be 0. What about theta? This gets swung in the direction of increasing theta, and so we go with theta equals 0 up to theta equals pi over 2. So our job is to find I squared, who is the integral from 0 to infinity on x and y of e to the minus x squared plus y squared as a quantity, and it was a dx dy, and what we're discovering is that we can do it as an r dr d theta, replacing the dx dy with that, inside x squared plus y squared is r squared, so it would be an e to the minus r squared, and we just figured out the bounds are 0 to infinity on r and 0 to pi over 2 on theta. We can execute that integral. Let u be equal to minus r squared. Du should be minus 2r dr. Minus a half of du will take the place of r dr, and you'll be integrating minus a half e to the u du to get minus 1/2 e to the u. And so that's going to be converted back to be minus 1/2 e to the minus r squared, which we are going to write as minus 1 over 2e to the r squared. Now we can't plug in infinity. What we have to do is put a variable placeholder and let that variable go to infinity. And yes, there's a still outside integral of 0 to pi over 2 and in theta. So we put a b in, and we get minus 1 over 2e to the b squared. And we put a 0 in, and we get minus 1 over 2e to the 0. Okay. And we're trying to figure out the limit as b goes off to infinity. And yes, there is still an outer integral that we have to worry about. But as b goes to infinity, b squared is very large, e to that is exponentially large. This is going to go to 0. And then we'd have the outcome be positive 1/2. And so the integral from 0 to pi over 2 of d theta is just pi over 2. And with that half factor, what we're getting is that I squared is pi over 4. Okay. Which in turn would mean that I, taking the square root, is the square root of pi, and that whole thing is divided by 2. Okay. The answer to A is square root of pi over 2. In part B, they have the limit of this. This actually is a function that's given the name ERF. It's an error function, ERF, E-R-F, and we want to find out what happens as x goes to infinity on that. And so let me go to a new slide and have the limit as x goes to infinity of the integral from 0 to x, and then the dummy variable, there's an extra factor of 2 in there for this error function. E is to the minus t squared. That's all over root of pi dt. This is part B. Now we just figured out I, which was the integral from 0 to infinity of e to the minus t squared dt. We figured out that was the square root of pi over 2. Okay, and that is it can be written as the limit as x goes to infinity of 0 to x of e to the minus t squared dt. And so we almost have that. If you factor out this 2 over root pi, you'll have exactly the limit as x goes to infinity, 0 to x, e to the minus t squared dt. And that's supposed to be the square root of pi over 2, and that's times 2 over the square root of pi. The result then is that the error function goes to 1 as x goes to infinity. Okay. Comment down below if you have any questions.